Hello guys, welcome back to another video. And in this video we're going to be looking at arguably one of the most common equations in physics, and this is the simple equation of motion. V is equals to u plus at. What is v? V is the final velocity. What is u? U is the initial velocity. What is a? A is the acceleration, and t is the time. Time for what? Time taken to move from the initial velocity to the final velocity. Okay, so I'm going to get into the nitty-gritties of this equation. The purpose of this video is to show you how we derive this equation, not from the traditional approach where we use graphs, but from kind of a low-level thinking. If you are a programmer, it will be more like assembly language instead of using languages like Python. So we're going to be deriving this equation from a low-level kind of thinking, an untraditional approach. Now, in order to understand the equation we just wrote, I'll rewrite it again here. V is equal to u plus at. In order to understand this equation, you have to really understand what A means. If you watched the previous video where I was talking about force and Newton's second law, then you'll get to understand that A, what we call the acceleration, is nothing more than the velocity imparted by a force in a single instant in time. Let's write instant here. A, what you call the acceleration of a body or mass, whatever you think about, is nothing but the velocity imparted by a force in a single instant in time. What am I saying? Say we've got a body moving in a certain instant, it's moving at 5 meters per second, and the acceleration is 2 meters per second. Then what we're saying is, if that body continues to be under the influence of the force F, which is responsible for the acceleration of 2 meters per second squared, what happens is, each instant that the force will be imparting a velocity of 2 to the body. So initially we had a velocity of 5. So what happens is, the following instant we would have a velocity of 7, meaning that the force would have imparted a velocity of 2, and the following instant would have a velocity of 9, meaning that the force would have imparted again a velocity of 2. So the acceleration, what you call the acceleration, yes, you can call it the rate of change of velocity with time, but a more intuitive approach, a more intuitive feel is to really picture it as a velocity, the velocity imparted by the force. However, it doesn't take the units of velocity, always bear that in mind. But for intuitive purposes, like for really picturing it, always bear in mind that it's nothing but the velocity imparted by the force F acting on the body. Now, with that in mind, we can now attack our equation. Now let's look at how motion occurs. Remember, in my previous videos, I touched on how motion is nothing but a discrete action, not a continuous action. So say this is a timeline. Say 1, okay, let's put a 0 there. 1, 2, 3, and say 4. Now, say we've got a particle here. Say we've got a particle here at the instant we're labeling as 0. This is just a label. Remember, this is just a label. At the instant we're labeling as 0, say our particle is here, and no force, it's not under the influence of any force. And then we apply a force F. Let's just call it F1. And then we apply a force F1, which imparts a velocity of 2 part lengths per part time. Again, you can picture this as 2 meters per second. It's okay. If you do not want to understand where this is coming from, you can go and watch my previous video on force and Newton's second law, or my video for a better understanding on space, time, and motion. Now, say we've got a force F1, which is acting on the body now. Now, initially, at time t is close to 0, it was at this single point. It wasn't moving. Now when we exert this force, This force in turn imparts this velocity here, which we are labeling as 2 part lengths per part time. So what then happens the following instant, because we've introduced this force? The following instant, the body moves 2 parts in space. That's why I write 2 parts length, 2 parts in space. So it arrives at this point. And the following, so this happens at this instant. Let's call it F1. This is where we introduce our force. So this instant aligns with this instant, and this instant aligns with this part. The following instant, if we keep applying our force F1, then, like I said, F1 will keep imparting the velocity 2, but now it's adding upon the previous velocity, or the initial velocity, if you will. So instead of landing on this point, it will land on 1, 2, 3, 4. Why 1, 2, 3, 4? 1, 2, because initially it had 2 part lengths per part time of velocity. But because the force F1 is still imparting this velocity, it will move another 2 in space. So it will move a total of 2 plus 2. And if we go on, this is for the instant where t is equal to 2. For t is equal to 3, we expect to get a velocity of 6 part lengths per part time. So this imparted velocity is what we are calling acceleration. This imparted velocity, when we come to the equations of motion, this is what we call the acceleration. Now I want to show you how we derive v is equal to a plus t. But I'm going to first look at a scenario where we do not include the initial velocity. Let me rub this again. Okay, so the first equation we're going to look at, or the first equation we're going to derive, is more of this form. V is equal to AT. Once you understand how we derive V is equal to AT, you'll be better able to understand the derivation of V is equal to U plus AT. It's just like what we did in the previous video, where we introduced the equation F is equal to MA, but argued that to understand this better, we have to first look at F is equal to A, and then move upwards, or move our way up. So the same applies here. Sorry. Here we're going to be moving our way down. So we're going to first introduce this, and then we'll later introduce this. Like we did in the former video, we introduced something simpler, and then we introduced last the equation, which is a bit more complicated. Okay, so let's see how we derive this equation. So again, I'm going to draw a similar diagram. That is a diagram similar to the one I just drawn right now. And again, I'm going to use a 0 here. 1, 2, 3. In our illustration, we're going to use force F1. And force F1 is going to impart velocity V1. Now say V1 again, like in the previous example, V1 is 2 part lengths per part time. Meaning, if initially our particle was here, and there wasn't any force introduced here, 0 force, and then in the following instant, we introduce F1. What happens is, this is going to go to 2, and this is going to go to 4. That is 2 parts in space, 1, 2, and after this following instant, it's going to go to 4 parts in space. Now, we can sort of like create a sequence to see how this is going to form in the end, like what is going to happen in the end. So initially, let's do this. Initially, we had 0 velocity here. Then after the following instant, we get a velocity of 1. And in the other instant, we get a velocity of what? V plus V. In this instant, that is here, The velocity is v plus v, which is what? Which is really 2v. And as we move forward, we'll get 3v, and so on, 4v, and so on, 5v. Now, I want you to look at something here. I want you to look at something. V represents the imparted velocity. Let me use the right label here. Put a little 1 here, the necessary ones. V1 is the imparted velocity. So what you're seeing here is the imparted velocity. But like I said, this is what we call the acceleration when we're now deriving the equation. This is the acceleration. Always keep that in mind. So I want you to look at something. We want to see a pattern in the values that follow, like after certain instance in time. At t is equals to 0, we've got 0. Note, at t is equal to 0, we've got 0 velocity. At t is equal to 1, we've got 1v1. Let's do this. At t is equal to 2, we've got 2v1. At t is equals to 3, we've got 3v1. You notice the pattern. So what this means is, if I want to get the velocity that's going to occur at, say, t is equal to 20, then using this pattern, this would occur at 20, sorry, the velocity would be 20 v1 for t is equals to 20. For t is equals to 40, like given that we keep maintaining this force, given that we keep maintaining this force, the velocity will be 20 v1 at t is equals to 20, 40 v1 at t is equals to 40. In other words, the velocity would be, let's do this, the velocity would be t v1 at time t. So if you simply plug in a value, say, like we have here, 20 in here, what you have to do then is plug the value again here, 20, so that we get the velocity 20 v1. So this is the formula we end up with for the velocity at any instant in time. At any instance in time. This is the formula for the velocity. Now, again, remember I said v1 is just the acceleration. So what this turns into, it then turns into this TA, but to make it more familiar, we write it as such, AT. So we've got V is equal to AT, which is this. Simple, right? Now we're going to move on to this point. Now I'm just going to wrap off this material. I'm not going to wrap the entire stuff off. I'll still keep this material. Now I want to look at how we then move to U. How do we introduce the U, the initial velocity? Now, let's keep on looking at this sequence. So at t is equals to 0, the object is here, or the particle is here, it's not moving, and then we introduce our force F1 at the following instance in time, and then it moves to this point due to the imparted velocity V1. After 2 instances in time, it moves 4 steps. That is, the initial velocity it got here 2 plus the imparted 4. 1, 2, 3, 4. 4 spaces. It moves 4 spaces in time. And then at 3, because it now has a velocity of 4, plus the imparted V1, which is 2, it moves 1, 2, 3, 4, 5, 6 spaces. Meaning its velocity here is 6 part length. That's 6 parts in length per part in time. Per part in time. Okay, so we now have V is equal to AT. But notice this. v is equal to at only works when we know the initial conditions, when we were there when the body was at zero velocity at first, and we like clicked our clock such that like we pressed our clock such that when the body began to move, it began to move simultaneously with the seconds or whatever units are on our clock or stopwatch. So this only works when we know what the initial velocity was, and that is 0. It only works when the initial velocity was 0. Now in the case where, say, we begin here, we do not know what happened in the past. This is the past. This is the past. And say all of a sudden, we want to derive the equation of the motion of this object, but we do not know what happened in the past. That is, because we do not know what happened in the past, a force, say F3, could have been imparted, which moved the particle 1, 2, 3 spaces in places in space, or a force of 1, 2, 3, 4, 5, 6. A force F6 could have been imparted, which moved the object. Or I'm saying F6 just to make it coincide, but not necessarily F6 could be any force in general, but generally a force that brings about an imparted velocity of 6 part lengths per part time. It could have been imparted at this instant and got the object here. So when we're this side now, we do not know what happened. We do not know how the object got here, how the object got to this point where it has a velocity of 4 part lengths per part time. So I then asked, find the equation of the motion given that we have an object which is moving at a velocity of 4 part length per part time at this instant in time. However, let me write this. However, this is not all. We've got an object moving at 4 part lengths per part time, but there is a presence of a force F1. So these are the conditions. We're asked to find the equation of the motion of this object, given that we have a force F1 acting on this object. And initially, like when we look at this, initially it has a velocity of 4 part length per part time, or you can make that 4 meters per second, whatever works for you. So this is the instance, this is the scenario we now want to work with. How do we derive an equation in this case? In the case where it started from 0, it was easy. We simply got an equation where v was equal to at. But in this case, now I'll spoil it a bit. In this case, that's where we get this equation where v is equal to u plus at. But we want to show that now. Okay, so we've got an initial velocity of 4 part lengths per part time. So if we create a similar sequence like the one we did previously, we would get something like this. 4 is our what? Is our initial velocity. This is, we're creating the sequence. What is the following velocity after like the following instance? Like in the following instance, what is the following velocity? Remember, F1 is imparting a velocity V1. So the following velocity will be 4 plus V1. And in the following instance, we're going to get 4 plus 2V1. You get it? Let me put this in brackets to make it clear a bit. In the following instance, we're going to get 4 plus 3V1. Why am I always putting the plus? Why am I saying 4 plus X number V1? The reason I'm saying that is we've got an initial, like the first moment we looked at this, the initial velocity was 4. But we know that F is responsible for adding a certain velocity every instance in time. And what is that velocity? That velocity is V1. So when we look at it at first, it's at 4. But after we move a certain part in time, it goes to v4 plus v1, because in the following instance the velocity of v1 will be imparted by the force F1. In the following now, this is going to be the initial velocity, and we're going to add another v, which brings us to 2v1, and so forth, 3v1, going on and on and on. Again, we're going to repeat the same procedure we repeated. At this point, we're going to label it as t is equal to 0. This point, we're going to label it as t is equal to 0, like this instance in time, we're going to label it as t is equal to 0. So we've got a velocity of 4 at t is equal to 0, and we've got a velocity of 4 plus v1 at t1, t is equal to 1, and a velocity of 4 plus 2v1 at t is equal to 2, and a velocity of 4 plus 3v1 at what? At t is equal to 3. Now again, notice, this is 1. 4 plus 1v1, 4 plus 2v1, 4 plus 3v1. And in this scenario, this is similar to just writing 4 plus 0v1. So we've got, for t is equal to 0, we've got on the right side 0v1, 1v1, 2v1, and we've got a 2 here, 3v1, and we've got a 3 here. So what we can simply do is write this for the velocity at a time t. The velocity at time t will then be 4 plus tv1. This would then be the velocity at time t. But remember, v1 is simply the acceleration. So this is simply equal to this. 4 plus at. Can you see it? 4 plus at. This a is simply the v1. The t is this t. We simply rearrange the terms in the expression. Okay, look at this now. 4 is the initial velocity. Now it's easy to see that if the initial velocity wasn't 4 and was 10, if we don't change the force F1, the force F1 will keep imparting the velocity v1. So in this case, we replace 4 with 10, 10, 10, 10, meaning the velocity at time t will be equal to 10 plus at. So arbitrarily, given any velocity, like any velocity whatsoever, as the initial, let's call the velocity now u. What we'll then have is the following instant, the force F1 is going to impart a velocity of v1. So we'd have u plus 0v1, u plus 1v1, u plus 2v1, u plus 3v1, u plus tv1, and in the end what we have is u plus at, a being the replacement of v1. v1 and a are simply the same thing. A is the acceleration, v1 is the acceleration. I'll repeat, a is the acceleration, v1 is the acceleration. v1 is the imparted velocity due to f1, but acceleration is just a fancy name we use for it, and we change the units to meters per second squared to make it that fancy. So this is the velocity at time t, which is what we wanted to begin with. V is equals to u plus at. So this is the non-traditional approach of deriving the equation of motion. V is equal to u plus at. Okay, so that's it, ladies and gentlemen. I hope you enjoyed the video. Please leave a like, subscribe, and comment if you did. And I deeply hope that this video has helped someone. It has helped open someone's thinking in terms of physics. Thank you, ladies and gentlemen. Have a good one. stay motivated.